We have a turbine. It's in steady state. It tells you the amount of power. It tells you the mass flow rate. And it gives you okay, so I'll set that up. It looks like you're going to need to use tables for it. Oh. CV2. Okay. Okay, it's first law for control volumes. We're on number 2. And it says it's an insulated steady state turbine. Since this is first law for control volumes, we know we're starting with this equation, d dt is equal to Q dot for the CV minus W dot for the CV plus, I'll just write it as M dot since it's steady state, times the quantity HI plus VI squared over 2 plus GZI minus M dot times the quantity HE plus VE squared over 2 plus GZE. Steady state, so dEdt goes away. Insulated, so there's no heat transfer. And let's see what else it says. Neglecting potential energy effects. And it tells us that W is 23 megawatts, so 23 times 10 to the 6 watts. And the flow rate is 40 kilograms per second. So potential goes away. We can work to the other side, and that was 23 times 10 to the 6 watts is equal to 40 times the quantity HI plus, it gives us the speed at either the inlet or the exit, both. So it enters at 35 meters per second and exits at 120. So now we're down to one equation with 2 variables. And it says that it exits as a saturated vapor at 0.06 bar. Well, since it's a saturated vapor, the pressure by itself is enough to look up any other properties. So you can look up the specific enthalpy at that pressure. Okay, so this is saturated at 0.06 bar. So you can look this up. And that lets you solve for the enthalpy at the inlet. And once you calculate that enthalpy at the inlet, then you can do sort of a reverse lookup to get the pressure at the inlet. Okay. Any other homework questions?
Number 4.
Okay. So solve for HI. And then reverse lookup for the pressure. I think it's possible that we've done both of these in class already. I take a look back at class and see if you can find those notes. I think maybe we already did that. Any other homework questions?
I know I have one.
Okay.
Let me see. Oh yeah, number 5. I think I did it right. I just want to make sure.
Of this set that we're looking at right here?
Yeah, the one or I should say for the current homework, power, refrigeration.
Oh, okay. I'll do that one today.
Okay.
I'm going to do a few of those problems since there's no solutions posted.
Okay.
So why don't I just get into those then?
I also just wanted to make sure with number 5, the coils, how it gives you a temperature for the coils.
Yeah.
The whole idea that you neglect that because it's part of the system that.
Yes.
Okay.
Yes.
So I was looking at that for a while. I'm like,
I was too, actually, but
that makes sense.
But yeah, all that matters. We'll get to that. We'll get to that. Yeah. But yes, what matters is the reservoir temperature.
Yeah, because the coils aren't a reservoir. They're
right.
part of the system doing work.
Right.
Okay.
Okay, so there are no solutions for these. So let's go through a few of these problems for power, refrigeration, and heat pump cycles. Number 1. Sort of asks, is this thing possible? Is it possible to create a cycle that receives energy QC from a cold reservoir and ejects heat QH to a hot reservoir and does work on the surroundings. Well, this is just sort of a conceptual question, but it connects to the Clausius statement. There's no way to make a cycle that moves energy from a cold reservoir to a hot reservoir without inputting other types of energy into the cycle. And so there's no way that you can move energy from the cold to the hot and still be outputting work. Yeah, question.
All right, hold on. The thing I saw in different than this, like there were, I don't know, for a period of time there was a question like that there, but when I checked it in like at a later time, there was a completely different set of questions.
Really?
Yeah, that was calculation-based questions rather than conceptual ones.
That's what you have.
Well, I think, yeah, just with one, you can answer calculation-based or conceptually.
Hey, what? Okay, that
That doesn't look like the problem set you've been using.
no, there was none of these ABC stuff.
Huh.
I don't know. I'll have to check back.
Okay, yeah.
Maybe.
Yes, email me what you have or something.
Yeah.
But the idea is just to move heat from cold to hot. You have to input energy into the system. So this is impossible. And then number 2, 2 through 6 all are sort of similar to each other, I think. You're basically going to be using 2 things. You're going to be using the equations for performance and ideal performance. And you're going to be using the first law. So for number 2, it's a power cycle. So work is coming out. Here's the hot reservoir, and it's putting heat into the system. Here's the cold reservoir, and heat is being ejected there. And so if you look at the directions of those arrows, you can see that QH has to be equal to W plus QC. We know that TH we're given in the problem is 1000 Kelvin. And TC is given as 300 Kelvin. And so, and then A, B, and C, it just gives you different values of work or heat in or whatever. So are these possible? So the first one says QH is 600 kilojoules. The work is 300 kilojoules. And QC is 300 kilojoules. Let's do one that's, well, I guess on this one, I'm going to do all three of these. So the second one, QH, is 400 kilojoules. The work is 280. And QC is 120. And then the third one, QH, is 700. W is 300. And QC is 500. Okay, well, since we're given these input temperatures, we can calculate the ideal performance of this power cycle. So the ideal efficiency is, think about, to come up with these off the top of your head, think about what each of these cycles is trying to generate and what's the sort of input cost of it. For the power cycle, you're trying to get work out of it. The cost is, heating up the boiler. Man, this is going crazy today. So the efficiency is work over QH. Well, we're given the work. I guess first, well, let's check this first since I already wrote it. So the work is 300 kilojoules. The heat coming in at the boiler is 600. Oh, I didn't, sorry. So for the ideal, it's going to be 1 minus TC over TH. So that's 1 minus 300 over 1,000. So that's 0.7.
Yeah, because what you had before, the W over QH, that's the actual.
That's the actual, yeah.
Okay.
I was
a little confused.
getting ahead of myself. Sorry about that. Okay, so to get the actual then, and I mean, we're just going to be comparing the actual to the ideal, and then also comparing, looking at the numbers and making sure that it makes sense with the first law. So this is equal to work over QH, which is 300 kilojoules over 600 kilojoules. So that's 0.5. Check the first law, and you get that 600 is equal to 300 plus 300. That works. And so both of these combined tell you that the performance is less than ideal. So is this reversible, irreversible, or impossible? This has irreversibilities in it. It's not an ideal cycle. Then for part B, first law says 700 is equal to 300 plus 500. This is QH work, and QC, that's obviously not true. So we don't have to go any further. You can't have a cycle like this. Okay, let's save this one. So B, let's look at the first law. So it says 400 is equal to 280 plus 120. This one works. So then we'll go to the performance, and that's W over QH. So 280 over 400. And $280 over 400. So that is 0.7. So it's possible. It has the same performance as the ideal. So this is a reversible power cycle. And then the last one doesn't satisfy the first law, so you don't have to go any farther than that. Let's go to number 4. So this one says a power cycle. Okay, so it's a power cycle. The high temperature reservoir, we're just saying has a temperature T. We don't know what that is. And the low temperature reservoir is 280 Kelvin. And it develops 40 kilowatts of power. And we know that it rejects 1,000 kilojoules per minute of energy to the cold reservoir. Well, everything else we're doing is in kilowatts, so we'd like to express that in kilowatts. So divide 1,000 kilojoules per minute by 60 to give you kilojoules per second. That's kilowatts. And that is 16.6 repeating kilowatts. And here's QH. Okay, well, the first law says QH. And by the way, you do have to be careful with whether you're doing it on a rate basis or on a absolute, joules basis. I sort of have them mixed here. If I'm doing all of my powers in watts, then this has to be on a rate basis. You can also think of this same stuff as, kilowatts is kilojoules per second. So you just think of it as a cycle over a second and then just drop all that and use the equations that you're used to.
Yeah, it's conservation of energy and conservation of power, pretty much the same thing.
Yes. But like, notice I could think of this as happening over 1 second, and then just think of that as 40 kilojoules, 16.6 kilojoules, and then I wouldn't have to write everything with the dots. But be careful about that. You don't want to mix those two up. So QH dot is equal to W dot plus QC dot. And so QH dot has to be 56.6 repeating kilowatts. And now it's asking for the minimum theoretical value of T. Well, remember that for a reversible ideal power cycle, one minus QC over QH is equal to 1 minus TC over TH. We know now what all those powers are. And so we can plug those in and just calculate that TH. So 1 minus 16.6 repeating over 56.6 repeating is equal to 1 minus 280 over T. And so T is equal to 56.6 repeating times 280 over 16.6 repeating. Can someone tell me what that is?
I got 952, I believe. Got 10.
Okay, 952 Kelvin. Any questions about that one? But really just notice that for all of the things in 2 and in 4, and the one we skipped, number 3, the approach is the same. There's really only 2 things. There's the first law, and then there's the equations for the performance. Let me do 5, and then that's the last one I'll do. Okay, so this is a refrigerator. It's in steady state. The coefficient of performance is 4.5. And remember, the coefficient of performance for a refrigerator is what you're trying to do is get a lot of heat removed, a lot of heat QC removed from the cold reservoir, and you're trying to input as little work as possible. So a high performance would be a high QC over a low work. You want to make that number as big as possible. Our work is 0.8 kilowatts. And the temperature that heat is ejected to is 20 degrees Celsius. So at the hot reservoir, the coils are 28 degrees Celsius, but the reservoir itself is 20 degrees Celsius. And we want to figure out the rate at which, so we're trying to figure out QH dot, how fast heat is being rejected to the surroundings. And then second, what's the lowest theoretical temperature inside the refrigerator? So what's the lowest theoretical TC? A refrigeration cycle looks like this. You have work coming in, and that work is being used to move heat QC from the low temperature reservoir and move heat to the high temperature reservoir, an amount QH. And so even though the directions are reversed from a power cycle, the directions still tell us QH has to be equal to QC plus W. And that's all true on a per time basis too. Okay, well, we're given that the performance is 4.5, and that's equal to QC over W. So that's QC over, we're given the work input, 0.8 kilowatts. And so then you can calculate QC dot is 0.8 times 4.5. What's that? 32, 36, yeah. 3.6 kilowatts. We're trying to find QH dot, but now we can use the first law.
I was about to say, I was like, why didn't I just replace work, or I should say the QC term in there with QH minus W, right?
Right. Okay. Yep. So QH is equal to 3.6 plus 0.8. So 4.4 kilowatts. And now if you had a perfect refrigerator, perfect efficiency, no irreversibilities, what's the lowest theoretical temperature that you could have? And what we're looking for is the temperature Tc. Well, we know that in a reversible cycle, QC over QH, we can think of these as dotted, is equal to TC over TH. So 3.6 over 4.4 is equal to TC over, and this is what Marshall asked at the beginning, it gives two temperatures at the high temperature reservoir. It gives the temperature of the coils and it gives the temperature of the reservoir itself. What we care about is the temperature of the reservoir itself. It's only inefficiencies that keep those coils from being the same temperature as the reservoir. And so that's 20 degrees Celsius. Remember that you have to put that in Kelvin, so that's 293. And so Tc is equal to 3.6 over 4.4 times 293. And what do you get for that? 239.7 Kelvin.
I got 239.85. Or, I forgot why I added the 293.15.
0.15, yeah.
Okay, that makes sense. Yeah, it was one of those yesterday. I'm just staring at it. I'm like, I don't get it. I don't get it. And then I grew up, going from the system doing work to the coils to and I was like, wait a second, draw a box between that.
Yeah, right.
Doing work in the coils.
Yes,
and I'm like,
that's right. Yeah, yeah. No, I thought about that for a while.
Just
yeah.
To conceptualize
yes.
What's actually going on. They don't care about what's going on internally.
Right.
Just the reservoir.
Yes.
The work going in.
Yep.
The cycle, like the thing that you drew for that's why the first one was impossible, right? Because it's putting the work into it instead of.
Yes, that's right. That's right. I mentioned this once in class before, but it was just sort of in passing. So I just want to make sure everyone sort of understands how this works when you look at it. Because, we talk about adding energy or and you make the heat move from the cold to the hot. But just conceptually, the way that works is if you have an insulated container, like an insulated cylinder and a piston, and you push the piston down, the temperature of the gas inside goes up. And if you lift the piston up, the temperature inside goes down. So you can imagine, you could have it wouldn't be the greatest system, but you could have a refrigerator that was just you walking back and forth from a hot region to a cold region with this piston and pressing it down and then putting it in thermal contact with the hot region and getting energy. Putting it in thermal contact with the cold region, like the inside of the refrigerator, getting the energy to flow into that gas. Now, as you hold it down, you walk out, run to the other room, the hot place, and you let the piston rise, the temperature goes down, put it in thermal contact with the room, and that energy is ejected into the room. And now you run back to the inside of the refrigerator, push it down. So that's sort of the principle of how a refrigeration system works.
Wait, wouldn't it be pulled up at the refrigerator? Because it would cool off, be cooler than your cold reservoir. Then you take that.
I did it backwards, didn't I?
Okay.
Yes. So yes, right. You go into the refrigerator, you pull up, it gets cold. Heat, now the refrigerator is actually hotter than the gas. It flows into the gas. Now you run over, compress it down, it gets really hot. That lets you eject it into the room temperature. You could do it with just a gas like that.
You just have to pull up fast enough that it's colder than your cold reservoir, and then slam down fast enough that it's hotter than your hot reservoir.
As long as it's, yeah, I guess if you consider insulation to be the problem, then yeah, you got to do it quick. So there's not a lot of, but you can make it a lot more efficient if instead of air or something, because I'm imagining this happening with air, but if instead you devise this refrigerant that is right near its saturation temperature and pressure, and so when you remove energy from it, it changes from a saturated gas to a saturated liquid. And then when you add energy to it, it goes from a saturated liquid to a saturated gas. Now you haven't changed the temperatures at all because you're at that phase change temperature.
Okay, but you did change.
But you've allowed for a lot more transfer of energy to happen with each one of those cycles.
Okay, that makes sense. Yeah, I remember vaguely in the past when I first learned this, just from the physics standpoint, so they didn't actually talk about like refrigerants or anything. With just the cycles.
Right.
So when it's like kind of detached from something conceptually,
yeah,
it's hard to visualize.
So yeah, so that's what makes a refrigerant better than than air.
Okay.
Yeah.
That's kind of what we talked about.
Okay. Any other questions about those?
One last question. I just want to make sure I got it right for both, not just power cycles, but heat pumps and refrigerators. Reversibility is always dependent upon ideal performance or ideal efficiency. Like for example, in number 6C, the focus on performance of a reversible heat pump cycle operating between hot and cold reservoirs at these temperatures, it's always just going to be for it to be reversible, it has to be running ideally.
Yes,
okay.
That's right. Okay, so the next thing I want to talk about is using entropy to determine directionality. In a process. Conservation of energy can't do that. It can only tell you that two different instances have the same temperature, but it can't tell you which was first and which was second. This is going to allow us to determine what's happening forward in time. Okay, so we'll be using isolated systems. An isolated system means there's no material transfer across the boundary. Second, no energy transfer across the boundary. So think of a rigid insulated container. Then if this is the case, if your system is isolated, the change in entropy for your system is some positive value sigma, greater than or equal to 0. So you can think of this as the entropy statement of the second law of thermodynamics. So I'm going to do a couple examples. I'm going to do one with a solid that you drop into a liquid. There are different temperatures. We'll calculate the entropy changes for both of those things. You imagine those two things being inside an insulated cooler or something, so you don't have to worry about energy transfer. Well, so let's say that the steel is hot that you drop in and the water is cooler. Over time, what you would expect to happen is that both of them are going to reach some temperature in between their two initial temperatures. What you don't expect to happen is to drop steel into water at the same temperature and have them move apart to different temperatures. The first law of thermodynamics doesn't see any problem with that, but obviously we know that that can't happen. The second law, though, is what will tell us, no, it's impossible to take these two things at the same temperature and have them, one get hot and one get cold. The only possible direction that this can happen is two things being at different temperatures and coming to the same temperature. Okay. Well, I'm going to do the first one, these two examples. I'm going to do the first one with a solid and a liquid. And so we're going to treat both of those as incompressible. And remember from the TDS equations, we came up with expressions for the change in entropy for incompressible materials. So we can use that approximation. And then if we have time today, or else next class, I'll do an example with gases, and we'll use the ideal gas, same idea, but with ideal gas approximation of the change in entropy. Okay, so let's say you have an isolated system. With half a kilogram of steel at 400 Kelvin and 10 kilograms of water liquid at 283 Kelvin. So what we want to do is first calculate the equilibrium temperature of this system. And then second, use the second law to show which is the final state. So you can just look up these values. Remember, for incompressible materials, CP and CV just both reduce to what we call C, and that's DUD temperature. You can look these up for these two materials. For water, it's 4186 joules per kilogram Kelvin. And for steel, it's 460 joules per kilogram Kelvin. Well, the total change in internal energy is the change in internal energy of the water plus the change in internal energy of the steel. So for the water, that's the mass of water that we have times the change in the specific internal energy. And notice that from this definition of C, we can rearrange that and get du is equal to C dt. And if you integrate both sides of that equation, you get that the change in U is equal to C times the change in temperature. So for the water, we have 10 kilograms. And we're going to multiply that by the specific heat times the change in temperature. So what's our final temperature going to be? That's what we're looking for. And so we can just call that T. Our initial temperature is 283 Kelvin. I guess I could have just done this in Celsius, but and now calculate for the steel. That's half a kilogram times its specific heat times, if we're looking for the temperature where these two, the temperature that these both come to, so we're going to end up at the same temperature T, although the steel's starting at 400 Kelvin. And now since this is rigid, well, it's isolated, so there's no transfer of energy, we know that this total change in internal energy is going to be 0. So we can add these two up and set them equal to 0. There's one variable, so you can solve for T. And I think what you get is 283.6. That's funny. Well, it's a lot more water, and water has a much bigger specific heat. So 283.6 Kelvin. Way, way closer to the temperature of the water than the temperature of the steel. Everybody with me on that? If you did any kind of thermodynamic stuff in Physics 1, I'm sure you did this a calculation like this. But the thing that you haven't seen before now is that there's no change in energy between these two, but that means you could go back and forth from one to the other and there would be no change in energy. So now we're going to use the entropy statement of the second law to determine that it's possible to go from the two different temperatures to the final same temperature. It's impossible to go from the final same temperature to the two different temperatures. Okay, so the total change in entropy is equal to the change in entropy of the water plus the change in entropy of the steel. And that's the mass of the water times the change in specific entropy of the water plus the mass of the steel times the change in the specific entropy of the steel. For an incompressible material, the change in specific entropy is equal to C times the natural log of T2 over T1. So the total change in entropy is the mass of the water times the specific heat of the water, 4186, times the natural log of the final temperature, 283.6, divided by the starting temperature of the water, 283. And now the same thing for the steel, so the mass, 0.5, times the specific heat of 460, times the natural log of the final temperature, 283.6, over 400. And you get a change in entropy of positive 9.56 joules per Kelvin. The change in entropy is positive so this way is possible. What if you check the other way now? Is it possible to go from the same temperature to 283 Kelvin and 400 Kelvin. Well, notice the only thing you'd be changing there is you'd be changing what you're calling T1 and T2, so you'd just be changing that fraction. So your change in entropy would be 10 times 4186 times natural log of 283 over 283.6 plus 0.5 times 460 times the natural log of, this time our final temperature for the steel would be 400 over 283.6. And the natural log of the reciprocal just gives you a negative, so you get the change in entropy in this case is negative 9.56. That's negative, so that's not possible. Any questions about that? One thing that's really important to notice is that this is for an entire isolated system. You cannot apply this to individual elements of a system. If you, well, let's see.
Yeah, because in this case, the entropy of the steel went down. And
Exactly.
Water went up.
Exactly. So the different pieces of this system, you know, something is likely to go down, something is likely to go up. It's the whole isolated system added up together that has to be positive. Okay. Or like, yeah, like in a refrigerator, you know, you're decreasing the temperature of the cool region. That's decreasing the entropy in there. But the trade-off is that you're adding heat to the higher temperature, and you're doing that at a higher rate than you're removing entropy from the inside.
Adding more entropy to the universe than you want to take away.
Yeah, right. I think next time I'll start with the same example, same idea, but let me just draw out the example. So let's say that you have this rigid container. And it's full of, you know, cool air. And then you have this one little section that's full of hot air. At a higher pressure. And then you open this container, let those two mix. And we're going to do the same thing. Find the equilibrium temperature and show that it's possible for them to equilibrate, to come to the same temperature, but it's impossible for them to start out at the same temperature and go to a hot region and a cool region. It obviously makes sense with your intuition, but this is how you calculate it. Okay, that's all.
Just one unrelated comment. I like the statistical interpretation. The second